Bismillah ar-Rahman ar-Rahim. This is a steel structures class delivered by Dr. Qusay Al-Kaseasbeh from Mutah University on April 7th, 2020. Today, inshallah, we're going to continue with chapter 5 and the classifications of the beam shapes. If you remember in chapter 4, when we did categorize the compression members into cylinder or non-cylinder shapes, I told you for the beams, we're gonna classify them, or the beams, or categorize them into compact, non-compact, or cylinder shapes. So it might be compact, non-compact, or cylinder shapes. That depends on the width to thickness ratios, which is lambda. Okay, here is lambda. So right now we will have width to thickness ratio for the cross-sectional shape, and let's say that for wide flange, for the flange is going to be BF or sub F dividing by 2T sub F, and BF, TF are the width of the flange and the thickness of the flange respectively. Okay, and for the width, it's going to be H dividing by T sub W, and H is the height, and T sub W is the thickness of the width. So this is just an example which or what is lambda. And every cross-sectional shape, it has its lambda. So this lambda, it will be in a comparison with lambda sub P and lambda sub R. Lambda sub P is the upper limit for compact category. So if lambda is less than or equal lambda P, so that means the shape is compact. Okay. So here lambda less than or equal lambda P. P here is the limit. So if we less than this limit, so we can say the section is compact. If we are greater than this limit, the section is non-compact, but it will be limited by lambda R here. Lambda R is the upper limit for non-compact category. So if lambda is less than this, so we still have the possibility to be compact or non-compact. After that, it will be cylinder. So here, once again, lambda is less than lambda P, it's compact. If lambda is greater than lambda P, less than or equal lambda R, so the shape is non-compact. And for each these two categories, we have a different design procedure. Okay. If lambda is greater than lambda sub R here, the shape is cylinder, and it's not, sometimes, okay, we can design the cylinder shapes for the beams, but it's not preferable. So avoid them as much as you can. يعني designers بيحاولوا يتجنبوا cylinder cross sections. Okay, and the category is based on the worst width to thickness ratio here. So lambda, so let's say in wide flange, we do have lambda for the flange, as I showed you here, and lambda for the width. If one of these are non-compact, so the whole cross-section is non-compact. Yani if the flange is non-compact and the width is compact, the cross-sectional is non-compact. If the width non-compact and the flange compact, the section is non-compact. If both non-compact, that's for sure the section is non-compact. Okay, so let's move down. In table for the compression members, I showed you table B for 1A, and for the beam, we're gonna show you tables B for 1B. It's gonna be just a table to show you the limits, which is lambda P, lambda R for each of the cross sections. And let's go there and show you this table, okay? So, okay guys, this is table B for 1B, okay? which is rigid thickness ratios, compression elements, member subjected to flexion, okay, which is bending here as a beams. So here we're gonna have like stiff, unstiffened, stiffened elements as we did have in B1A or 4.1A. So here, this is the lambda, okay? And for the flange, wide flange, this is B, which is equal B sub F dividing by 2 dividing by T, okay, for the flange. So this is lambda P, which is the compact, non-compact border. So as I mentioned, if lambda is less than this much for the wide flange, it's for the flange actually here, it's going to be non-compact or compact. If greater than this, it's going to be non-compact, but should be less than lambda r. So these are the limits you have to use to classify or categorize the beam shapes into compact, non-compact, or cylinder shapes. And you will find for different shapes here. And for the stiffened element, which is, let's say, the whip here for the wide flange, we have these values, and here is the lambda for the wide flange because this is the most common ones. But we do have four different shapes. This is C, this is HSS, and so we have different shapes. If you notice here, guys, same formulas are using for the wide flange and for the C channel, except here it's going to be same here, but in the flange we will not, the B is going to be different, okay? The B here is going to be different for this one here, and here is going to be different, but we'll say use the same formulas. Okay, let's get back to the textbook. This table is extracted from the tables I just showed you in the steel manual, which is B4 1.1b, just for the wide flange, or let's say I shapes here. Okay, in flexor actually, in bending, okay? So it's gonna be same values. This is lambda, lambda P, and lambda R. This is for the flange, this is for the whip, and these the formulas we're gonna use, okay? So let's start with bending strength of compact shapes. So first we will try to find the bending strength for compact shapes. Compact shapes when lambda is less than lambda sub P or equal. Okay, so let's see how that goes. Let's clean up here and move down. So for the compact shapes, the beam might fail by reaching these limits. First of them, reaching here, guys, reaching the plastic moment, which is MP, okay? And all the cross section making or becoming fully plastic. If you remember this guy, sorry. So the section here is fully plastic, and this is the maximum moment capacity the beam can get. So all the other capacity under different, let's say, conditions will be less than plastic moment. So when the beam will get plastic moment, if the beam is stable enough to get this point. يعني البيم مستحيل أو من الصعب جدا يصل البلاستيك مومنت إلا إذا كان مدعم بشكل جيد، وهي أعلى قيمة ممكن يصلها البيم. Okay. The second one, it might be, so let's assume this is 1, and this is 2, this is 3, this is 4. Let's call them 4 ones. It might fail if reach the lateral torsional buckling, and this is LTB, stands for lateral torsional buckling. It might be elastically or inelastically, and I'll show you what does it mean, elastic or inelastic. And the third one, it might fail under flange local buckling. Okay, this is FLB, and same, it's under elastic or inelastic behavior. And the fourth one is whip local buckling, which is WLB. It might be elastic or inelastic. So what does it mean to say elastic or inelastic? So if the buckling occurs when the maximum bending stress is less than the proportional limit, So we can tell it's elastic. So if you remember guys here, this is a stress strain diagram. So let's say this is for ductile steel. So here we do have a proportional limit. So if the bending stress is happening here before getting the proportional limit, so we will tell it's elastic. If it's happened after that, this is a plastic or inelastic. Okay. And for the first step we need to do, guys, we need to categorize the beam as compact or non-compact or cylinder, okay? So this is going to be our first step when we are calculating the moment capacity of the beam, okay? And then we can find the moment resistance or the moment capacity. This section is going to apply for two types of beam, okay? The first one is hot rolled I shapes, pinned about the strong axis and loaded in the plane of the weak axis. So it's going to be for I shapes, okay? And the second cross section here is going to be for channels pinned about the strong axis and either loaded through the shear center or restrained against the twisting. The shear center, as you know, guys, is the point on the cross section through which the transverse load must pass if the beam is to bend without twisting. So here is the point where the load can pass without doing a twisting, okay? And as I mentioned to you, these will, because let's say these, the lambda P, lambda R limits, they are same for I shapes and C shapes, except for the flange. It's going to be P or B over T for the C, and it's going to be BF over 2TF for the I shapes. Okay, you will see that later. And the other thing, Shabab, the whip is all the time compact in I shapes and C channels listed in the steel manual if Fy is greater than 65 KSI. Let me show you this in the textbook and highlight this again. So here, and sometimes guys, if it's mentioned to you that here guys, they mentioned to you that if the flange is continuously connected to the whip, that means it's compact. You will see that in the examples, and here are the same let's say limits we did use later or previously. So the whip criterion is met by all standard I and C shapes listed in the manual. So for any I shapes or C shapes in the steel manuals, they will be compact if Fy is less than or equal 65 KSI. Yani you can directly judge, okay, the whip is going to be compact if Fy is less than or equal 65 KSI. Okay, actually this is for I shape and C shapes. Okay, so you will see this in some examples. So in such cases, you just need to check the flanges. But for built-up sections, it's going to be different because you are just combining plates or hot rolled with the plates and so on. There is one very important note that the compression members have a different criteria than flexure members. Yani, what we have for columns is really different what we have for the beams. So the shape, it might be compact for beams or flexure, but it's not going to be cylinder for the compression. يعني نفس الكروس section ممكن يكون نصنفه cylinder. Let's say if this is a column with a cross section wide flange, let's say 18 by something. ممكن هذا يكون cylinder للcompression، ممكن يكون compact للبيم، لأنه we do have a different criteria، معايير مختلفة بين ال flexure members وال compression members. Flexure members which means beams. Let's continue with this, just to clean this up and continue. So as I mentioned to you, if the beam is compact here and has continuous lateral support, okay, or if the embraced length is very short, the nominal strength or moment strength, which is Mn here, is going to be the full plastic moment of the shape, which is MP. يعني راح تكون M النومينال strength بتساوي ال MP. إذا كان عندنا ال unbraced length is very short. راح نشوف شو ال unbraced length. So unbraced length, if we do have a beam here, so this is unbraced length. So okay, which is the point or the length between 2 points of bracing. If we do have another joint here, so this is unbraced length, and this is another unbraced length. We will pick the largest one. So, and I'll show you the sketch for that. For members with inadequate lateral support, يعني lateral support مش كافي أو مش مناسب, it's improperly, let's say improperly here. يعني مش مناسب, is not good enough, improperly. So the moment resistance is limited by lateral torsional buckling strength. It might be elastic or inelastic. Okay, so let me show you the sketch and then comment on that. So here is the nominal moment strength, okay, against the unbraced length. Let me show you what does unbraced length again in two different beams. These two beams, guys. So this is a beam. This is the point of bracing. يعني مثبتين بهاي النقاط, فهذا راح يكون ال unbraced length. If we do have another point here, so this is going to be unbraced length, okay, and so on. So in this one, figure 5.13, the nominal strength is a function of unbraced length. This is unbraced, okay, length. Okay, so here, if the beam is adequately or properly restrained or supported, يعني supports يعني very nice, so the Mn is equal the plastic moment. راح البيم يوصل the fully plastic section, راح يضل يحمل load لما يصير كل السكشن plastic. So here, in this case, if and here we mentioned just if the impressed length is very short, nominal strength is equal this much, so we do have adequate lateral support. And here, because just let me do that, not this way. So Mn here is equal MP, okay? And MP, as we taught you last time, was Fy times Z. And this is the plastic section or the plastic moment resistance or capacity. So for the member with let's say inadequate or improperly lateral supported, the moment resistance is limited by lateral torsional buckling. Here it might be inelastic and here it might be elastic. So if L is less than LP, so here it's compact. If L greater than LP, or this is equal, less than LR, this is non-compact here. If L is greater than LR, so here we can tell it's cylinder one, okay? Let's see how is the procedure to find the nominal flexure strength or nominal moment strength for the compact shapes. And here, once again, I'm just talking about I and C shaped sections. Okay. So this is very nice summary. And this summary just for here, compact I and C shaped sections. Make a big underline here. So if unbraced length, I just called L there, but let's call it LB here, okay? Unbraced length in the figure I just showed you, the one is like this, okay? So because this is LB, not just L, okay? So if LB is less than LP or equal that, so the nominal strength is equal to the plastic strength as I just showed you, and this one is equal Fy times Z. Fy is the yield stress and Z is the plastic suction modulus. If LB, which is unbraced length, okay, this is unbraced length in between LP and LR, so the moment or capacity or nominal moment capacity is equal to this equation. Or just let me do one thing here. It's equal to this equation, and the result should be less than or equal plastic moment. And if it's greater than this much راح ناخذ ايش الMP. We're gonna take MP. Okay, لأنه we told you the maximum value is this value, which is MP. If the section is properly supported or laterally supported. If LB, which is unbraced length, is greater than LR, MN is equal F critical times elastic suction modulus, and this value should be less than the plastic suction modulus here. And F critical is this much, guys. This is F critical. And there are like many parameters here. I'll define them for you later. Okay, so that's what we need to just memorize, or you don't need to memorize this. You will have this as an open sheet with you in the exam. So this is in case of the unbraced length is less than LP, and this if we have the unbraced length in between LP and LR, and this if we have the unbraced length is greater than LR, and this is the F critical here. So, okay guys, here the F critical is the elastic buckling stress, and this is the equation as I just showed you, and this is a stress, so it should be KSI. And let me define the parameters for you. This unbraced length in inch, okay? And this one is going to be clear for you, so you can get it easily from the question or the problem. Moment of inertia about the weak axis of the cross section, IY, which is here. Okay, and this we can get it from the manual. G is the shear modulus of the structural steel, which is this much. It's 11,200 KSI. This is G. And J is the torsional constant, okay? And this one you can get it from the table 1.1 in the part 1 from the steel manual, and this is 2 inch to power 4. There is an equation to do that, but don't panic yourself with this. You can get it easily from the manual. C sub W, it's warping constant. It's to power inch to power 6. Okay. And what else we do have? These. We do have anything else here? No. And this one is Young's modulus. We know it. This is elastic section modulus. We know it. And that's it for this one. Let's move down and see the other parameters. For the other parameters, this one, which is C sub P, which you will use it here, its factor accounts for non-uniform bending within the unbraced length PC. This factor will show you how to do it in example 4 or 5.4, and this is R sub TS square, and this is also you can get it from the manual. You don't need to use this one because it's going to be headache. Okay, and we do have C here. Okay, C is equal 1 for doubly symmetric I shapes. Okay, and it's equal this much here if for other let's say channels. And here guys, okay, this is for other channels, and each node here you can get it from the manual, which is the distance between the flange and flange centroids, which is this much, but you can get it from the manual directly. I'm just trying to check if there is any parameters not defined yet. I think we are okay. Let's show you how to calculate C sub P here and what is the formula for that. For these guys, L sub R, which is this equation, you didn't need to do it. I can show you how to get them from the manual easily because this is going to be a bunch of calculations. And same here, okay? So we'll show you later how to get these ones. Let's move on and see. So this formula, guys, will help you to calculate the C sub B, which is the factor accounts for gradient moment. If we do have a moment, if you do have a beam here, let's say we do have this beam, and the moment is, let's say, uniform. If the moment is uniform, CB is equal 1, and I'll show you here how or what does this mean. If it's not, if it's non-uniform, the moment, and the moment you can do it by, let's say, basic statics, okay? So here it's going to be 12.5 maximum moment. The absolute value of the maximum moment might be negative positive, and this is including the end points of unbraced length. يعني راح يكون عندنا مثلا هون braced length، اوكي؟ يعني خلينا نفترض هون عندنا braced length، فهاي راح تكون ال B. فالمومنت هون كم بيساوي؟ أعلى قيمة للمومنت هون مثلا قديش تكون من هون لهون، أوكي؟ dividing by 2.5 max نفس القيمة اللي هون plus 3 plus 4 MB plus 3 MC. MA is absolute value of the moment at the quarter point from the embrace length. يعني إذا عندنا embrace length هون بنقسمه هذا لإيش؟ 1 quarter المسافة هاي ربع، بعدين MB المسافة بالنص، بعدين MC المسافة على 3 quarters. يعني once again here guys. So this is a beam, which means this is the embrace length, LB. So a maximum moment, which is M max, it might be anywhere, okay? أقصى قيمة أو أعلى قيمة. MA هون الربع وهون النص وهون الثلاث أرباع. طبعا this is ربع LB وهون نصف LB وهون 3 quarters of LB. فبنوجد المومنت اللي هو MA وهون MB وهون MC. By this we can calculate the CB. There is a table. I'll show you how to get CB also directly from the table. Here, if we have uniform bending moment, uniform bending moment, that means it's equal everywhere, here and here and the maximum. So let's assume it's equal M. So this one M, they will cancel each other. So this is 12.5. This is going to be 12.5. 12.5 divided by 12.5 is going to be 1. So by this we can get the CB for the unbraced beam. So okay, this is the table 3.1, the values for C sub B for simply supported beams. Okay, this is for simply supported beams. So this is the load here. This is the lateral bracing along the span. So in this case, if you see that in this case, if we have non-bracing for this one here, it's going to be this much. And here, if we do have load at the load points, we do have bracing, it's going to be this much. Same here, we have different loading conditions. And I would like to show you this one here. If we have a simply supported beam loaded with a distributed load, if we have no bracing, it's going to be this much, because this bracing, just once again, guys, this is lateral bracing along the span. يعني هل عندنا أي bracing هون أو هون مثلا أو يعني so on. So if we get back here to this one, if we do have non-bracing somewhere here, so this is going to be 1.5. If we do have a bracing at the middle here, that this is the best way to show you, it's going to be 1.3, 1.3 CP. If we do have at 3 or third points here, we do have bracing here, so sub or CP is going to be this much, or this much, or this much for each of these. At quarter points, so same, we do have these values and so on, يعني which is سهل جدا تحصلوهم سي بي إذا كان simply supported beam بهاي الحالة. يعني هون نفس الشيء يا شباب حتى نكون أوضح، هون كانوا none, if none مثلا or at the load points هون none مثلا كانوا بس هون وهون، ما فيش عندنا أي شيء هون في this much، هون إنه في البوينت لود هاي لود بوينت نفس الشيء. طبعا هاي none كمان it's gonna be this much. يعني هاي الحالة العامة وهاي حالات البريسنج. I'll send you this table, okay, or upload it to the Microsoft Teams. Let me show you how to get some parameters that I just defined for you. So this is the wide flange shapes. So here we do have area, we do have depth, width, flange, width and thickness, and so on. Let's go to the next page for any section. So this is the compact section criteria I showed you in the last chapter, or chapter number 4. So here is the parameters I showed you that I told you, and I told you it's here, available here in the steel manual. This is R sub TS, this is H node, this is J, this is warping parameter, and all of them are available here. In addition to the moment of inertia about any axis, and Z and many other, and Z and C, S here, sorry, they are available for any section here. Okay, so right now let's move to example 5.4 on page 206 and show you how we're gonna calculate the moment capacity for a beam. Okay, so example 5.4. Determine the flexure strength of the wide flange 14 by 68 of A242 steel subjected to. The first one, continuous lateral support, and that means we have like a proper lateral support, and I mentioned to you what does this mean. Or we do have an unbraced length of 20 feet within or with CP is 1, when CP is given to you, or the lateral or unbraced length is equal 30, CP is equal 1, unbraced length which is LP, and this is in the case in B is equal 20 feet, and in case C it's equal 30 feet. So they're going to be the same solution, but we're going to get different things. So the first step should be to check the cylinderness or compactness of this cross section. So here, to check the compactness of this cross section, we need to do it for the flange, and we need to do it for the web. And web, we can expect that how much, or if it's compact or not. But let's see how we're gonna do that. For the flange, we need to get this value, which is B sub F dividing by TF from the manual. And let me show you how to get that. And and I'll get also H dividing by TW for the same cross section. So our cross section is 14 by 68. Let's go to the manual and see how we can get these values and make a comparison. And we need to get two limits, which is lambda P, lambda R for the wide flange. Let me show you how to do that. So if you go to the part 1 of the steel manual on page 24 here, guys, you will see our interested here, our interested cross section, which is this one here, this one. Okay, so this one here, guys, it's 14 by 68, and here what we can get, there is B sub F, T sub F, but we don't need to use that. So let's move down to the next page and see how much the compactness here, guys. So this is 14 by 68. So in this case, this is the BF dividing by 2TF. For this section is 6.97, and this is for the width, which is 27 point or 27, yeah, 0.5. And we can get Z here because we will need Z, the plastic section modulus for this one. And at some point we will need to get S. So all these information are available here, and we do have some other information here, and we will see if we need them in this equation. Okay, so these two values, and we got these values. We need to get lambda P and lambda R from the table B 4.1b. Okay, let me show you this table. Okay, from this table, which is this is the lambda for the flange. Once again, guys, this is BF dividing by 2TF, because this is the B here, and B, this is the half of the BF. So we need to check with this limit and this limit if we need. If it's less than this, so we don't need to do this. If it's greater than this, we need to check if it's still smaller than this or greater than this. And this is for the flange. And same thing we need to do for the width here, guys. This case, okay? For the width is going to be in this case, so that's what we got from the manual. And we need to check with lambda P here and lambda R if we need to do that. Okay, let's get back to our example and apply all these info to continue. So okay, here, this is the lambda for the flange, what we got from table 1.1 and 6.97 and that, okay. In comparison with the limit, which is lambda P here, 0.38 square root Young's modulus, which is 29,000 dividing by Fy, or the yield stress here is going to be equal 50 KSI. Okay, and this one is 9.15, which is greater than this, means lambda is less than lambda P. Lambda is 6.97 from the manual, and that we just calculated lambda P is this. So the section is, or let's say the flange is compact, okay? The flange is compact. If we do that same for the width, and we don't need to do that, but let me show you how to do it. It's H dividing by this one, which is equal, or the width thickness, which is equal to this much, and we got this from the manual, and I showed you how to do that, in comparison with 3.67 or 76, sorry, Young's modulus, 19,000 dividing by 50, and this one is 90.55, and this one is less than this, means that web is compact. Do we need to check the web? No, because I told you for I shapes and for C channels, the web is going to be compact if Fy is less than 65 KSI, and Fy here is 50, so it's going to be web. If you remember in chapter 4, I mentioned to you, if you see a C footnote across along the web, along the section, let's say if we do have, let's say like this, 68, there is a footnote here. If you see it and read the footnote, you will see that this section is cylinder if Fy is 50. For our section, this not there مش موجودة. Our section is compact. Since the flange is compact, the whip is compact, so the section is compact. So right now we can go further and calculate these three questions. Okay, so let's just me clean up here. In the first one, it told you that there is a continuous lateral support, means the cross section is fully supported and properly supported, يعني مدعوم بطريقة ممتازة. In this case, Mn is equal MP, and MP is equal Fy times Z. Fy is given, and Z we got it from the table. Let's show you the value here. So here is Mn, because the beam, and here is the justification, okay, التبرير, okay, because the beam is compact and laterally support, the nominal strength is Mn is equal M, or the plastic moment, which is Fy times Zx, because it's mentioned to you that it's depending about X. So this is going to be 50, and 115, I showed you from the table 1.1 how we got it, and this much is going to be 5,750 kip inch. Dividing by 12, it's going to be 479.2 kip foot. Okay, it's going to be the same if you say foot kip or kip foot, it's okay. Right now, using the LRFD method, this is the nominal. This is nominal. Okay, nominal flexor. It's not the design. The design strength for LRFD method is going to be phi beam here, or bending. This is going to be 0.9 times the value we got here. Okay, this is the value. So this one is equal 431 kip foot. And if we need to calculate the allowable moment strength, which is for the ASD method, this one is going to be here, guys. A nominal strength is going to be a nominal strength, which the one that we calculated here, okay, dividing by 1.67, this is the safety factor for ASD method, and this one is equal 288 kip foot. So right now, we did calculate if there is a continuous lateral support, section compact و properly supported, بنحل على هذا الأساس، okay، اللي هو بالمنطقة هاي. اوكي، بالمنطقة هاي اللي هي أعلى قيمة ممكن نحصلها. Okay. So the question number 2 or B, let's say, if it tells you that how much the moment capacity if the unbraced length is equal 20 feet, okay, and it gives you CP is equal 1. In this case, if you remember, so okay, this table 3.2 for wide flange, and this one is just to select the cross section by Zx, but we're gonna use it here in different way. So Fy is 50. That's what we need to know, to pick, and this is the wide flange, and our section is 14 by 68. This is the Zx that we got from the manual, and same value here. And here we need to get LP and LR. LP is equal 8.69, and this is equal 29.3. We need to make a comparison because it told us LB is 20 feet, right? So LP is 8.69. okay, طبعا in feet, LR is this much, 29.3 feet. So LP is in between. So that means LP is greater than LP, less than LR. So here we're gonna have inelastic lateral torsional buckling control. Okay, let me go back to the example and show you what does this mean and which formula we should use. Since we got LP from the table 2, we don't need to use this formula because it's gonna be headache for you guys, okay? So we will just here, we don't need to use this one, which is gonna be the same value here. It's almost same value, okay? And we can just get them directly from the table 3.2. And this is same for LR, because if you're gonna calculate LR, you have to do all of these to come up with LR, and look at how much the formula for LR is panic, okay? So you don't need to do that. We got this from the, which is this much. And I think they will get this much here. Look at this, yep, it's almost this one here. We got it at 29.3 feet, which is nothing. So that this is our case here. That means we need to use this formula, okay? Because of this condition. If LP less than LB less than LP استخدمناها ب A فأوجدنا أنها هي البلاستيك moment. On we need to calculate this one. This one is given to us as 1. If it's not, you have to calculate it from its formula. P, the plastic one, which is Fy times Z, we calculate it in A, which is this much, which is kip in inch, minus, open a bracket, MP, which is the same value for this, 0.7 Fy is given to us, and this one I showed you from table 1.1, it's 103 SX, and this one it's LP, which is unbraced length, minus LP, which is the one that we just got it, either from the formula here, but I didn't recommend you to get it, or from the table 3.2, and I have to send you this table. And same here, this is LR and this is LP. Doing that, this much is going to be 4,572 kip inch. Dividing by 12, we'll get this value 381 kip foot. And this one should be less than the plastic moment, which is this much. This much is equal to this much, guys, but this is divided by 12. Will get you this much, okay? So don't get confused, because this is kip foot, this is kip inch. So right now we got the nominal strength, which is here, this one. This is the nominal strength. If this one greater than this, take this. إذا هاي كانت أكبر من هاي فخذ البلاستيك moment. So the design strength here is 0.9 times this for LRFD method. For ASD method, this one dividing by 1.67, which will be 0.6, times this is equal 229 kip foot. Okay, so this is the B. For C, it's going to be the same procedure, but it might be different case here. Okay, let's move on and see how is that. For C, if you remember, C is the brace length is 30, and LR, we got it from the table 3.2, it's 29.3 foot. And here LB is greater than, just a minute, LB, which is 30, is greater than this much. So the section will use this formula here, because here the elastic lateral buckling will control elastic lateral buckling. Again, getting back to that shape here, here we do have plastic moment. Here lateral torsional buckling. Here gonna be inelastic اللي case B, وهاي case A بالنسبة لنا، وcase C بده يكون lateral torsional buckling elastic. Okay, in this case we're gonna use this formula. This S6 we got it from the manual 103, which is the same we just used in B. But F critical, we need to get F critical. F critical, this one it's given to us. This is okay. This is given. LP, which is here, LP in foot. Just you need to convert it to inch, multiply 12. And this is RTS. You will get it from the manual, table 1.1. I showed you table 1.1. We can get RTS. 1 plus this much. J is there. C here is 1 for wide flange or doubly symmetric is 1. Okay. If it's not, I showed you the formula how to do it. And this is each node from table 1.1, and this value is same to this value. And this is the elastic buckling stress, which is F critical. This times here, Fs will get you the nominal strength in kip inch, dividing by 12, you will get it in kip foot, which is 291. And this one all the time should be less than or equal the plastic moment. If not, if this greater than this, take this, okay? In this case, okay, we are okay. For Al-Rabdi method, this is gonna be 0.9 times this, here it's gonna be 262. And same for ASD method, we will just dividing this one here, this value by 1.67, and you will get it this much. Okay, guys, so by this we can calculate the nominal strength for compact shapes. For non-compact shapes, we can have a different procedure. So the summary I showed you, it's very easy to follow up with. So that I think it's going to be much easier to just follow this summary and check the compactness first. And let's get back to the summary and show you that again quickly. So yeah, this is the summary. First of all, just this is for compact I shape and C shape. So if LP is less than LP, LB less than LP, اللي هو plastic section modulus or plastic moment. So this is going to be Fy times Z. This is case A كان بالنسبة لنا. وذيس case B بالنسبة لنا وحلينا على هذا الشيء ووجدنا هذا هو اللي هون شباب نفسه اللي هون اوكي. وهون وجدنا هاي من التيبل 3 2 ودائما لازم يكونوا اقل من ام بي. وهون بالكيس الثالثي لما كانت عندنا اف اللي هو هون البي is greater than الار فالnominal strength is this much ولازم تكون اقل من هاي وهاي الفورمولا. So by this you can get the nominal strength for compact I and C shapes. Thank you guys for your watching, and please, if you do have any questions, chat with me on Microsoft Teams or send me an email. Thank you. يعطيكم العافية.